Archimedes' principle. There's a famous story that goes along with Archimedes discovering this principle. The king gave him a crown, and the king had suspected that the goldsmith that made the crown had stolen. That's not right. Back up to the beginning of the story. So with Archimedes' principle, there's this story where the king, a Greek king, had asked a goldsmith to make a crown for him, gave him the gold, paid him to do the work, and then suspected that the crown that he got back was gold-plated and not actually gold all the way through, and he suspected that the goldsmith had stolen the gold or the extra gold and kept it for himself as profit. But the king wanted to know whether or not the crown was actual gold without destroying the crown, and he challenged Archimedes to do this. Archimedes was known as a mathematician and a casual scientist and a natural philosopher and such, and he put his thoughts to the problem, and allegedly one day he climbed into a bathtub, and when he climbed into the bathtub where the water had been drawn and the water sloshed out of the outside, he registered that a way to figure out if the crown was what it actually should be, if it was the right materials. And so he jumped up out of the tub and ran down the streets naked through town screaming "Eureka," meaning "I've got it," or "I found it," or "I figured it out," and then actually did the test, and it turned out that the crown was not real. So the goldsmith was jailed, if not killed, and Archimedes was honored for having solved the problem. Your textbook refers to Archimedes' principle as the principle of flotation, but basically Archimedes' principle. But with Archimedes' principle, I'd like to think about it both in terms of objects that float and in terms of objects that sink. So for an object that sinks, the buoyant force upward is equal to the weight of the fluid displaced. So you have this object that sinks, it pushes some fluid out of the way, but there's still a buoyant force upward from that fluid, even though the object sinks. And this object then that sank will appear to lose weight, and the amount of weight it loses is equal to the mass of the volume of fluid it displaced. Also, the volume of fluid displaced is equal to the volume of the object itself. And so you've done this many times before, where you've measured irregularly shaped objects of volume by just dropping them in water and reading how much the graduated cylinder reading went up. On the other hand, for an object that floats, the weight of the fluid displaced, and therefore the buoyant force, is equal to the weight of the object. So now the volume of fluid displaced isn't equal to the volume of the object. Instead, the volume of fluid displaced is equal to the weight of the object. And an important number here again is the weight density of water, which is 10,000 newtons per meter cubed. By the way, of course, that's fresh water. It's slightly more if you're looking at something like salt water for the ocean. Anyway, buoyancy is related to or dealing with objects floating, but to buoy is to lift an object up, or the lifting force of a fluid that's causing an object to float. Buoyancy then refers to or relates to the apparent loss of weight that you have on an object when it is floating or submerged in water. And buoyant force is the net upward force exerted on the submerged object. And this is kind of just restating Archimedes' principle here, but for floating, the buoyant force is equal to the weight of the object, and for sinking, the buoyant force is equal to the apparent weight change of the object. Finally, here we're going to end with gases, the final state of matter that we're going to concern ourselves with. Gas is a state of matter, again, that has no fixed shape or volume. Air pressure is equal to the weight of the air above the surface, and so there are lots of different standard pressures, different pressure systems used to measure pressure. In chemistry, the most common one that we use is atmospheres. However, there are others: millimeters of mercury, bars, pascals, which is the common metric one. However, pascals tend to be tiny, so we tend to go for kilopascals, and pascals, kilopascals are related to newtons per meter squared. And then there's, of course, the English one, pounds per square inch, or PSI, and all of those can be used as ratios when doing conversions or calculations, but we tend to use pascals, kilopascals in physics. Anyway, for those of you that have chemistry, you'll recall the gas laws. For those of you that haven't had chemistry, these may be new to you. However, you do not need to know whose name goes with whose law here in physics. It's important for chemistry, especially because these guys were all famous chemists who did other things along the way as well. Here in physics, you need to know the laws and the principles that go with them, but not the names of the scientists that go with them. Anyway, Charles's law, named after Jacques Charles, states that volume is directly proportional to temperature. That is, if you heat up a gas, then its volume is going to increase. If you cool a gas, its volume is going to decrease. Boyle's law, named after Robert Boyle, says that volume is inversely proportional to pressure. So as you increase the pressure, you decrease the volume on an object. If you can increase the volume of a gas, then you decrease the pressure on it. That those two are inversely proportional. Opposite things happen. Gay-Lussac's, which I believe is named after John or Joseph Gay-Lussac's, says that pressure is directly proportional to temperature. So as you warm up a gas, you increase the pressure. If you cool down the gas, you decrease the pressure. With all three of those laws, Charles were assuming pressure stays constant, Boyle's were assuming temperature stays constant, and Gay-Lussac's were assuming volume stays constant. We're assuming the third term there does not change. There are other gas laws that are used specifically in chemistry, but those are the ones that are important for physics. This brings us to the idea or common or combined gas law. P1 times V1 over T1 equals P2 times V2 over T2, where P, V, and T are pressure, volume, and temperature, and 1 is an initial state and 2 is a final state for our gas. And so we're taking a gas and we're changing one or more of the properties on it and seeing how that affects the other properties on it. You'll notice that the two that are inversely proportional are in the numerator together. That's Boyle's law, pressure and volume. For the ones that are directly proportional, pressure and temperature, or volume and temperature, that those two, you have 1 in the numerator and 1 in the denominator. And mathematically it works out that way. One thing I will point out, all the units have to be the same, so the pressures have to be in the same units, the volumes have to be in the same units, the temperatures have to be in the same units, and the temperatures absolutely must be in an absolute scale. They must be in Kelvin. They cannot be in Celsius. Try the numbers. They just don't work out. They have to be in a non-negative numbering system that is Kelvin. Anyway, there are other gas laws, but they're not too important for here in physics. And the nice thing is you can really think through these. And I'll give you an analogy in class about how I tend to think through these, and we'll play with the gas laws if time allows. Anyway, another interesting gas principle is Bernoulli's principle, and it says that when a fluid moves at a higher speed, the pressure it exerts is decreased. This also means that if you restrict the path of flow of a fluid, it will increase the flow speed. So this is why when you put your finger over the end of a hose, the water will spray further, because you're restricting the opening. You're actually because of that, then the same volume of fluid is trying to make it through the hose still, and so then it has to move faster to do that, and as it moves faster, the pressure that the fluid can exert decreases. This is part of why an airplane flies, though there's an XKCD comic that if I haven't shown you at this point in the year, I'll show you now, that has to do with why this isn't the complete picture. But it does turn out that air moves faster over an airfoil or a wing because it has a larger surface to go over, or a larger direction to go over, and so then because of that it moves a little bit faster. You have less air pressure here, low pressure here, high pressure here, and you end up pushing the wing up. But it's not a complete picture. You have a homework question that refers to it, and as I said, there's a comic I'll toss up here on the screen. So this one here, I can't always recommend XKCD because sometimes it's inappropriate for school, but this is one of my favorites. And so you, of course, could read the comic, but I'm going to go ahead and read it off here because it applies to what we're talking about. Handling a student who challenges your expertise with an insightful question. So, kids, the air above the wing travels a longer distance, so it has to go faster to keep up. The faster air exerts less pressure, so the wing is lifted upwards. It's Bernoulli's principle, just like I was talking about. And then the insightful student says, but then why can planes fly upside down? And the teacher teacher has 3 responses here. The right response is, wow, that's a good question. Maybe the picture is simplified or wrong. We should learn more. And in reality it is, and we can explain it a little bit more, bringing in Newton's third law. And there's still some details that maybe are a little bit too advanced for us to cover, which is where the wrong answer, which unfortunately I'm sometimes guilty of, it's complicated and we need to move on, comes into play. And then a very wrong answer from the teacher here: Santa Claus is your parents. And so just totally off topic and trying to debunk the student another way. I hope that I haven't done that and don't do that to you. And please call me out when I use the wrong answer if necessary. But as often as possible, do search out other explanations and do understand that sometimes we are simplifying things down here. Anyway, that actually finishes the notes here today. Be sure if you have any questions that you jot them down and bring them with you to class.